Morning. In this session, I would like to demonstrate a reaction for which you have the kinetic rate law as per LHHW kinetics, Langmuir, Hinshelwood, Haugen-Watson correlation. So before we actually go into the problem, of course, some details about the problem statement are given here. Let me try to explain what actually is involved if you want to model LHHW kinetics in Aspen. Now, typically when you look at Aspen, it has got a built-in model to represent these kinetics given by Langmuir, Hinshelwood, Haugen-Watson. In short, we call it as LHHW kinetic model. Now, when you look at this LHHW kinetic model, as you are already aware, this kind of expressions will result, especially when you carry out gas phase reactions catalyzed by solids. So typically the rate laws are generally divided into three categories, three factors. The first one is known as the kinetic factor, and the second one is known as driving force, and the third one, whatever you have in the denominator, is known as absorption term. Now typically when you look at Aspen, there is a small issue. You need to express various constants involved in this rate law always in the form of this equation. Whatever is the constant that you have, ln kf is given by a plus b by t plus c ln t plus dt. Most often c and d would be 0 because we will be expressing the rate constant and its temperature dependency by either of these two forms. You know, these are similar to the ones that we have been handling even in power law models. This is going to express the temperature dependency of rate constant. This is known as the frequency factor, and this is your activation energy, which you are fairly aware of. But when you want to represent this kind of an equation in Aspen, you need to take logarithms. So the value of ln k, the frequency factor, will become a, and this will become the whatever value of e that you have, e by r will become the value of b, right? So you need to take care of this, especially when you are using Aspen to represent the Langmuir, Haugen-Watson, Langmuir, Hinshelwood, Haugen-Watson correlations. For a detailed description, you are advised to look at this book published by Wiley. The author is Kamal Al-Mala, Chemical Engineering Applications, Aspen Plus. He has provided a detailed explanation for representing these kinetics, giving certain examples. In fact, the example that we are going to deal with also has been provided by this book. So there are a few other things that we need to look at. Remember one important factor. You will not be able to directly write the values of frequency factor and activation energy. You need to take the logarithms and then provide the values of A, B, C, D as per this equation. Normally when you use the rate constant in this form, obviously C and D will be 0. Let us further expand this to... Now when you look at the driving force expression, typically those of you who are involved with reaction engineering would know there will be typically two terms. One is the forward reaction, the other one is the backward reaction if it happens to be reversible in nature. So you may have the concentrations of reactants expressed to some power and the concentration of products expressed to some power as per the kinetic model. Now this is how typically the rate equation, the driving force expression will have. So normally we expect the driving force expression to have two terms, the forward and the backward, but occasionally you may see in the driving force expression. So you can check up very clearly from the actual model that you are working with. So in the same way, absorption term, the number of steps involved in the mechanism for deriving these Langmuir, Haugen-Watson, Hinshelwood, Haugen-Watson correlation. So the number of terms associated with absorption term will be equal to the number of steps involved in the mechanism. Of course, when you write these equations, typically in the case of gas phase reactions catalyzed by solids, the basis usually would be partial pressure, but occasionally you may be using even molarity, mole fraction, and other variables as well. So be careful in choosing an appropriate basis for representing this concentration. Are you using molarity, partial pressure or something else. So this is one aspect that you may have to look at. And you know, the absorption term is likely to be raised to the power of certain value. Normally, this power will come into picture only when the reaction, the rate controlling step happens to be surface reaction. And in the case of surface reaction, if it is involving only one active site, this M will be equal to 1. And if it is involving two active sites, it will be equal to 2, and so on. If it involves three active sites, this will be 3. So you need to define this separately when you enter these kinetics in Aspen. Now let us look at the two possibilities. Take a generic equation which is reversible in nature. So now the rate expression can be something like this. When you want to consider the three terms, of course absorption expression I have not expanded yet. So let us concentrate on the numerator. Now this is what you mean by the kinetic term. So when you are defining, if you are writing this rate law in this form, you will be able to define the kinetic term. When you are defining this kinetic term, you need not have to take logarithms. Only when you want to represent the constants involved in driving force and absorption expression, be careful. This has to be done only with respect to the constants involved in driving force as well as absorption term. So if you are trying to write, if your rate equation in this form, you will be able to directly enter the value of frequency factor and activation energy, if this is the way you are trying to represent your rate law. And then we will be talking about this driving force term and absorption term separately. So if you have, in this case, you will be able to K and E directly in the kinetic form, as is given by this these values. Alternately, if you try to propose this equation in this form, you multiply this and write the rate law in this form. So for example, whatever is this rate constant multiplied by Kf, let us call this as K1, multiplied by Kf. Again, Kf will also be express its temperature dependency. And if you try to write it in this form, some other value Kf star and Kb star, that means Kf multiplied by this will be Kf star, and Kf multiplied by K star into e power minus e by RT is written as Kf star, and similarly Kb multiplied by K into e power minus R into 1 by T is written as Kb star. If you happen to write your rate law in this form, now what is the kinetic term? The kinetic term is 1. Now when you are trying to look at the kinetic term is 1, and you will have to take this as ln1 is equal to 0. So you need to enter A is equal to 0, B is equal to 0, C is equal to 0, and D is equal to 0. Sorry. You need to enter K is equal to 1. Sorry, I'm sorry here. Just one second. As I said, in the case of kinetic term, you need not have to take logarithms. So you will be able to write K is equal to 1. But remember, there is nothing like activation energy. So set activation energy is equal to 0. So especially when you have the rate law in this form, the kinetic term is equal to 1. So you should be able to enter K is equal to 1 and the activation energy is set to 0 because there is no E in the kinetic term. So try to be careful. So either in this way or in this way, you should be able to define your kinetic term. Accordingly, you should be able to enter this value in Aspen. Now let us come to the absorption term. There are two possibilities. The absorption term normally is expected to have two terms, but occasionally you may have only one term like this. So once again, if you try to write this expression in this way, or if you multiply inside, accordingly you can take care how to define the kinetic factor. Now let us look at the driving force term if you are writing it exactly in this way. Or if you multiply that this value inside, now the driving force term will be K into e power minus e by RT multiplied by concentration of W and concentration of X, whatever basis that you are choosing to express this concentration, either molarity or maybe partial pressure. In such a case, if you multiply that inside, again the kinetic term will be equal to 1 and you need to set it as 1 and activation energy is to be set to 0. But this is now, we have already addressed this form. Now we need to address this. For example, if you put your rate law in this form, define your kinetic term like this. This is done separately. Now when you go into your adsorption term, now whatever value of Kf that you have, you need to take logarithm as per this equation and calculate the values of A, B, C, D and enter the values of A, B, C, D, right? Or if you have exactly in this form, now what you need to do is in term 1, enter A is equal to 0. We have already taken care of this kinetic term if this is the way you have written. Now the constant for this first term is equal to 1, right? So Kf is equal to 1 and A is equal to 0 and also set B, C, D also equal to 0 and try to represent what is the power to which these concentrations are raised as per your driving force term. In this particular case, W and X are set to 1. The exponents of W and X are set to 1. They can be different. It could be 2, it could be 0.5, it could be any other value. Right? See, remember there are two possible ways. One way is the kinetic term may contain rate constant like this, or if you try to multiply inside, now the kinetic term can become 1. If it is 1, we saw what need to be done. You need to define K is equal to 1 and activation energy is equal to 0 in this particular case, right? Or if you write the kinetic term outside, then most often the constant for the first term in the driving force will be usually equal to 1. In such a case, you need to take care and the kinetic term you will be able to directly. Now what about the second term? Now you need to make this second term as 0. Now what is LNG? So in this case, you will have to provide a value of A is equal to minus infinity. Automatically the second term would be made 0. You may have a second term, but in case if you don't have a second term, what is this A in this expression? Remember when I am talking about A, B, C, D, I am always referring to this equation. So ln of minus infinity, ln of 0 is equal to minus infinity. So what would be the value of A? A should be given as minus infinity. So exponent of minus infinity will be equal to or will be tending to 0. And again, of course, in the case when you make this as 0, you don't have to worry about the exponents for these concentration terms. Anyway, they will be 0. So this is as far as driving force term is concerned. Now suppose you have both the terms associated with the driving force. What you need to do? So something like this. Now you need to, because the kinetic term here is 1. So I am going to define K is equal to 1 and E is equal to 0 as far as the kinetic term is concerned. After defining this, you need to go into driving force by pressing the driving force button in Aspen and you need to address term 1. Now whatever is the expression that you gave for Kf, now take it in this equation, calculate A and B, provide those values of A and B along with the corresponding exponents of W and X. Normally C and D will be 0. And the concentration exponent, depending on your driving force term, you need to enter those values. Now coming to the second term, you will have to choose the term 2 in the driving force because both terms are generally supposed to be there. Whether it is there or not, you need to define both term 1 as well as term 2 in driving force. So in the same way, you take whatever is the logarithm of this KB, calculate A and B, provide those values along with the exponents for the concentration terms. So that completes defining your driving force as far as Aspen is concerned. Now, usually in the case of adsorption term, they may have any number of terms depending on the number of steps involved in the mechanism for the chemical reaction, especially gas phase reactions catalyzed by solids. Suppose, assuming that there are 5 terms, now you take, usually the adsorption term will be in this form. The first term in the adsorption term will be always 1. So what do you mean by 1? So exponent of 0 is equal to 1 or ln1 is equal to 0. So you need to define A, B, C, D for term 1 as 0 because most often it would be 1, right? And first of all, identify what are the exponents with respect to these components. They may be anything. As an example, I just gave you. Sometimes you may have 2 terms coming into one particular term. You may have W and Y coming in term 2. In such a case, you define what is the exponent with respect to W as well as Y depending on the rate expression that you have. So these are the exponents which you can automatically obtain by looking at the rate equation in each of the terms. Remember, term 1 usually represents the first one, which usually is equal to 1. Now coming to the, now you may have some constant multiplied by the term 2. Now if it is having an expression of the form k into e power minus e by rt, again calculate a, b, c, d using this expression ln k ln kf is equal to a plus b by t plus e ln t dt and provide the values of a, b, c, d for each of these terms. That's how you will be able to enter the requisite information as per Aspen Plus. The only thing that you need to remember is the kinetic term can be entered as it is, provided you have the kinetic term involving a rate constant in the form k into e power minus e by rt. Suppose if the kinetic term is 1, define k is equal to 1 and the activation energy is equal to 0, because the kinetic term does not have any expression in the form e power minus e by rt. That could be one possibility, right? And coming to the driving force and absorption terms, we have seen what need to be done. See, typically it could be like this. So these are the exponents. For example, in term 2, we have both hydrogen and water coming into picture. This is an example taken from one of the worked out examples in that book, just to give you a clarification or idea. So you may have in each of the terms, many of these components might be represented. That depends on your rate law and the absorption term. Define these exponents by looking at your absorption term. Here there are 4 terms. The first term, as I said, is always 1. And you know, when the first term is 1, the constants a, b, c, d, because ln1 is equal to 0, that should be set to a is equal to 0, b is equal to 0, c is equal to 0, d is equal to 0. In the second term, why did you have only one constant? Probably you have some constant, let us say, some 2000 multiplied by, as you can see, partial pressure of water divided by partial pressure of hydrogen. So you are taking the logarithm of that constant. Now the moment you see 2 terms, there is k into e power minus e by rt, that kind of an expression for the constant for this concentration terms in both term 3 and term 4. So accordingly, you calculate those values and enter that information. Remember, the other rules similar to whatever you have followed while defining simple kinetics by power law model are also applicable here. The rate constant or the value of A is in the sense frequency factor, must always be specified in SI units, right? Take care of that. With this background, let us go back to the problem. Now you can see in this particular problem, the rate constant, of course, I might have multiplied this inside. I'll be writing this expression as 3.72 into 10 power 5 e power minus 21,700 by RT into CCH3Cl. So you have only one term, whereas the second term is equal to 0. And in the denominator, absorption term, you can 1, 2, 3. 3 terms in the denominator. The first term is always 1 usually, and the second term contains both A and B. When you take logarithm for this, so this value 5.97 into 10 power 3 will represent A, and 2440 by R will represent the value of B. Similarly, in the second term also, the constant A that you need to provide in Aspen will be equal to logarithm of 1.23 into 10 power 3, and this will be, B will be 5330 by R. And you can accordingly represent the concentrations. Now some data is given, the concentrations are in SI units, the value of K is in second to the power of -1 and E is in kilojoules per kilomole. And you were given that you need to preferred method of choice is unifact. The feed is entering at 100 degrees centigrade, 1 atmosphere, and these are the flow rates of the 3 components, reactants that are entering into the reactor. The reactor, a plug flow reactor, is operating at a temperature of 100 degrees centigrade. The configuration of the reactor is one single tube with a length of 2 meters and diameter of 1.5 inches. And you are using a solid catalyst. So choose catalyst present in the reactor, and particle density is given as 2000 kg per meter cube and void is as 0.5. We are also required to we are also required to carry out a sensitivity analysis to see the effect of both pressure and temperature on the mole fraction of HCl produced in the temperature range of 100 to 250 and pressure range of 0.5 to 6. Now let us see how to handle this problem in Aspen. So as is the case, first of all, we need to define the components that are involved in the problem, which are CHCl3, chloroform, and then water, and then oxygen. These are the three reactants in fact, and then carbon dioxide and HCl. So having defined the components, you can go to the next input step, choose a property model. We were given that UNIFAC is the preferred model for this problem. So let me choose UNIFAC, go to the next step, simulation environment, and create your flow sheet. The flow sheet is a simple reactor, a plug flow reactor, and output. Having done this, now we are supposed to specify the problem. So this is stream 1. We were given that the feed is entering at 10 degrees centigrade, a pressure of 1 atmosphere, and the flow rates are CHCl3 is 40 kilomoles per hour, water is also 40, oxygen is 20 kilomoles per hour. So we have defined the feed stream. Now we are supposed to address the reactor and reaction kinetics. So we were given that the reactor is operating at a specified temperature of, let me say constant at inlet temperature, because the feed is also entering at 100. So that will provide me a way to do the sensitivity analysis later. So we have given the specifications, then configuration. We are going to use only single tube. The length and diameter are provided to us. 2 meters is the length and 0.5 inches is the diameter. And it's a vapor phase reaction. So go to the next step, say new, R1. This is where you need to be careful. Earlier we have been choosing either power law or general model to represent the kinetics. Now I would like to choose LHHW kinetic model. Please address all these issues. By default it may not go. So click on pressure. We know the process stream is not at 0 pressure, but it is coming at 1 atmosphere. Of course, if you want to deal with pressure drop with respect to the process stream, you can say that, but I am assuming that there is no pressure drop, which may not be really valid. Remember, the flow has to take place across a packed bed of catalysts. Then you click on catalyst, choose this catalyst present in the reactor, and we were given the particle density as 2000 kg per meter cube, and then bed voltage is given as 0.5. Right? Most of the data with respect to reactor is done except for the reaction. We have not provided the kinetics. Now let us go to the next step. New. First of all, we define the stoichiometry, as is the case with any other model, any other kinetic model. So the stoichiometric coefficient for CHCl3 is 2, and then water also is 2, oxygen is 1. Products are CO2, 2, and HCl, 6. So this is our stoichiometry of the chemical reaction. Now we are supposed to address the kinetics. Now choose this as vapor. The rate basis is not volume. Choose it as catalyst weight. So this is what we need to address. First of all, we are addressing the kinetic factor. Now, as I said, the kinetic factor here is 1. You can refer back to this example. I'll put it maybe here. I am trying to write 1 into 3.72 into 10 power 5 e power minus 21,700 by RT into CCH3Cl. Now the concentration that we are using happen to be in concentrations only or molarity. Like in other cases, most often they could be partial pressures, usually in the case of gas phase reactions catalyzed by solids. Now, because the kinetic factor is 1, I am multiplying this inside, so the driving force will contain only one term, which is 3.72 into 10 power 5 multiplied by e power minus 21,700 by RT into CCH. So I am taking the kinetic factor as 1 and E is equal to 0. So the kinetic factor is addressed. Now, having addressed the kinetic factor, now go to the driving force. Now, you can once again look at I'll try to do it in two windows so that one second, so that you will be able to see it constantly. So the kinetic factor is 1. Now I am obviously there will be two terms that you need to address, term 1 and term 2. Molarity, or you can choose any one of them. Now in this particular case we are using concentration, so let me choose molarity itself. I don't change. Now you can see what is the driving force term 1. The constant is expressed, the exponent with respect to this concentration is 1 and all others are 0. There are no other concentrations coming into picture in the driving force term. So set this. Now this is what I was talking about, A, B, C, D. Now what is A, B, C, D? 3.72 into 10 power 5 multiplied by e power minus 21,700 by RT, right? So let us take these values. Now let me use a calculator to show you. Now the value of A, when you take logarithms, what will be the second term? Minus of 21,700 by R. So first of all, I can calculate that 21,700. Let me also divide this by the value of R, which is 8.314. Now that will give you minus, because of this sign, minus 2610.05. Let me put this as B, the second term after taking logarithms to this rate constant. The second term is taken care, and the first term is ln 3.72 into 10 power 5. So let us see this value. 3.72, take logarithm, multiplied by 5. So this will be the value of A. Right? So we have defined the exponents in the driving force term, term 1, and also the values of A and B depending on the rate constant. Take logarithm. Logarithm of 3.72 into 10 power 5 is 6.5686, and this will be minus of 21,700 by R, which will give you minus 2610.05 by T. In fact, in that expression, you are supposed to give A plus B by T. The values of A and B must be mentioned in that way. That takes care of term 1. What about term 2? You know, there is no term 2, which is equal to 0. So in this case, even the exponents, we don't have to worry because it is already 0. So you are supposed to enter a very large negative value. The maximum value that Aspen can take is something like this. So I am trying to provide that value, right? In fact, you don't even have to go to such a large number, but for safety, I am providing the largest negative number that is permitted. So that will take care of term 2. So we have defined term 1 and term 2 in the driving force term. So I'll be able to close it. Now you can go into the adsorption term. Remember, how many terms are there in adsorption? 3. 2, 3. So create 3 terms, and here also you create insert. Just 1 second, I think there was some problem. I'll continue from the saved file. Now onwards, because we don't have to restart from the beginning. Please bear with me. Again, opening that file. Let me go into the absorption term. So now, try to be careful. If you are able to understand what need to be given in Aspen, I think there should not be a problem. Now we have three terms. Now the first term is a constant 1. So ln1 is equal to 0. Obviously BCD will be 0. So for the first term, I am writing 0, 0, 0. The coefficients ABCD. These are ln k. So the ln1 is equal to 0. A is equal to 0. There are no other terms. And there is no exponent with respect to any of these components. Right? So 1 second, I'll come back. Just I would like to show you this. So that you will be able to put it this way. If you require, I'll show you. The first term is this, right? 1, which was addressed in adsorption term. Now the second term is 5.97. So the second term is something like this. 5.97 into 10 power 3. Okay? Multiplied by e power 2440 by RT. So let us look at that second term. Now, what is this? CHCl to the power of 1. So the exponent with respect to HCl is 1. Similarly, the exponent for the third term, you can see CHCl3 is also 1. So that's what I have provided. These are the exponents. Now, what about the constants for term 2? Now, take logarithm of 5.9 10 power 3 multiplied by e power 2440 by RT. So the value of B here will be 2440 by R. So let me calculate that. 2440 divided by 8.314. Sorry. So that is what I have entered. This is B by T. And similarly, what is the first value of A? ln 5.97 multiplied by 3. So that is 5.3602. In the same way, what about the second, third term? 10 power 3. So 1.23 ln is this value multiplied by 3. That will be 1. That is the value of A for the third term. And similarly, this one will be 5330 by 8.314. That is the value of B. 5330 divided by 8.314. Right? 6. 53. I think I might have made some mistake. 5330 by R. Did I enter correctly? 5330 divided by 8.314. 641. So I think I might have made some mistake. I'll enter this value. Let's see. So this is how you need to enter the information with respect to kinetic term, driving force term, and adsorption term, especially when you are using Aspen handling Langmuir, Hinshelwood, Haugen-Watson correlations. So having done this, now you can see all the input will be complete. You should be able to run the problem. So let me reset in case if I have some results earlier and run the simulation again. So you can see, of course, I was also using sensitivity analysis, so I'll explain to you later. Now let us look at the stream summary. Other things are similar to whatever you have been doing earlier. Now this is the CHCl3 that is entering. So 21.9069 is leaving, roughly about 50%, not exactly 50, slightly less than 50% conversion is happening at the given temperature and pressure. And similarly, HCl, so many kilomoles per hour of HCl is getting formed, right? Now we were asked to represent we were all asked to calculate the sensitivity analysis to see the effect of pressure and temperature on the mole fraction of HCl in product stream in this temperature range and pressure range. So that I have already created because the problem has terminated. I'm using it from the saved file. Now what I have done, you are trying to vary, first one, we are trying to vary the pressure of the reactor between 0.5 to 6 bar with an increment of 0.5. And similarly, the second is I am trying to vary the inlet temperature of the feed stream because the reactor is specified to operate at the inlet temperature itself between 100 to 250 in steps of 25. So these are the two variables that I am trying to vary. And what is that we are interested in looking at? So I am defining what is the molar flow rate of CHCl3 in the product. Flow of CHCl3 in the product stream. Product stream is nothing but the outlet, which is H2, right? And what I am trying to do, but from this I will be able to calculate the conversion. I know the inlet molar flow rate of CHCl3 is 40 kilomoles per hour, and this is the amount of CHCl3 I have in the output. So definition, conversion is equal to FA0, which is the inlet molar flow rate, minus the outlet molar flow rate of the same component. This will give you the number of moles converted divided by the number of moles emitted in the feed. So this will give you the conversion. That's what I am trying to plot. And if you run, the results are something like this. Of course, we are varying two variables. So first of all, it will try to keep the first variable constant and vary the second variable in its range. We are varying this between 100 to 250. So what is happening at a constant pressure, if you try to see, increasing temperature is increasing the conversion. Remember, this is the flow rate at the exit. So the flow rate at the exit is decreasing, that means conversion is increasing. Now, when you increase the pressure, even compared to 0.5 and 100, the conversion was 0.41, but at 1 and 100, the conversion was 0.5. So even increasing pressure increase the temperature. Of course, you can see the stoichiometry. From the stoichiometry, you can see, of course, we may not be able to judge this from the stoichiometry, but typically in the case of gas phase reactions catalyzed by solids, when you increase the pressure, what will happen? The partial pressure will increase, right? Mole fractions, the amount of CHCl3 is remaining the same, but as you keep on increasing the pressure, the partial pressures will increase. Always if you increase it beyond a particular limit, there can be an adverse effect because of the adsorption term. There may be a maximum also. Anyway, this is how we will be able to see the effect of temperature and pressure on the conversion. So let me plot this behavior. Just plotting the conversion. So now you can see, I think that so 100 keep on increasing the temperature, conversion is increasing. And similarly, when you increase the pressure, conversion is also increasing. Probably towards the latter part, there may not be a substantial increase, right? Conversion is more or less remaining constant or more or less coming to maybe a standard value, though there is a small increase. So now you can see from this chart that both temperature and pressure increase are favorable to have higher conversion of chloroform. So I think we are through with this. So please remember, let me just reiterate, when you come to especially providing the input with respect to the rate, especially following Hangman-Insel-Wood kinetics. So you need to choose the basis as catalyst weight, define the kinetic factor. In this particular case, the kinetic factor, there is nothing 1. So K is equal to 1, E is equal to 0. If you have some kind of a rate constant of the form K into E power minus E by RT, define the frequency factor and activation energy. While dealing with kinetic factor, you don't have to take logarithms. But when you are representing the rate constants within driving force term or adsorption term, you need to take the logarithm of the rate, whatever constant that you have, and provide the values of A, B, C, D as per this equation that I have already mentioned, as per this equation. So remember that the logarithms for all the constants involved within the driving force and adsorption term must be written by taking logarithms, calculating the values of A, B, C, D. But in the kinetic factor, you don't have to take logarithm. Remember that. Of course, you can multiply this kinetic factor inside the driving force expression. In such a case, the kinetic factor will become 1. And if you want to keep it outside, then you will be able to enter A and E, right? So that's what, in this particular case, what we have done, we have multiplied the kinetic factor into the driving force term and made the kinetic factor as 1. That's why I'm writing K is equal to 1, E is equal to 0. Now coming to the driving force term, generally there will be 2 terms, expected to have 2 terms. Of course, basis happen to be molarity and represent rate constant as you can see. So the power to the power of, the exponent with respect to this concentration is 1 and all other terms were missing. So they are write these values. 6.5686 is nothing but logarithm of 3.72 into 10 power 5. That is the value. And similarly, this has to be B by T. So 21 minus 21,700 by R is equal to minus 10. That's how I entered this information. And you know, the second term is actually 0. In order to make the second term as 0, you have to enter a large negative value for A that automatically makes the second term is equal to 0. E power minus this value is practically equal to 0. That's the logic in defining a very large negative value for A. And you don't have to worry about writing these exponents, right? This is as far as driving force term is concerned. For example, if you have term 2, and again, write the exponents depending on what are the concentrations that are represented in the second term and what are their exponents. And now, like what you did with respect to term 1, calculate A and B in case if it is not 0, the second term is not 0. That's how you will be able to address the adsorption term and come, adsorption term will be always, the number of terms associated with the adsorption will be equal to 1, right? And you know, the adsorption term in this particular case is expressed to the power of 1. So that is what is meant by this adsorption expression exponent. Now what are the various terms you have? 3 terms. The first one is usually 1 always, and in the second term we have HCl to the power of 1. So I have written in the second term the exponent for HCl as 1, others were 0. And in the third term we have concentration of CHCl3, exponent is equal to 1, right? Then what about the constants? Now what is meant by ln1? That is equal to 0. Obviously BCD also will be 0. And A for second term is ln 5.97 into 10 power 3. That value is 5.36. And 2440 by R is 293. And in the second term, third term, 10 power 3 is 0.621. 5330 by R is 641.8087. So this is how you will have to enter information with respect to LHHW kinetics. Once you do this, now the other things are common. So you will be able to do sensitivity analysis or whatever you wish. And we have seen the plot as well. So in this particular case, increasing temperature as well as pressure are beneficial with respect to the conversion of CHCl3, chloroform. So with these remarks, I would like to close this session.